We have rovers driving on Mars right now. We have a telescope that can photograph galaxies 13 billion light years away. We can track a spacecraft the size of a grand piano across 4 billion miles of empty space and communicate with it in real time. And yet, getting a probe to Pluto took 50 years of planning, and it arrived in 2015 for a single flyby that lasted a few hours. We still have never orbited it. We've never landed on it. And the nearest star outside our solar system is so far away that no propulsion technology we currently possess could reach it within a human lifetime. Why? What exactly makes these two destinations so fundamentally different from everything else we have explored? In this episode, we are going to break down exactly how you send something to Pluto, the gravity assists, the fuel math, the 9-year journey, and then we are going to scale all of that up to the nearest star. Because there is one problem with interstellar travel that almost nobody ever mentions, and it might be the hardest one of all. Pluto is a dwarf planet sitting at an average of 3.67 billion miles from the Sun. That distance alone is enough to make any mission extremely difficult. But distance is not the problem. The real problem is speed, and what you have to do to achieve it. To reach Pluto in any reasonable time frame, a spacecraft needs to leave Earth traveling at an enormous velocity. New Horizons, launched in 2006, left Earth at 36,000 miles per hour, the fastest departure speed ever achieved for a spacecraft leaving Earth. At that speed, you could travel from New York to Los Angeles in about 4 minutes. But carrying the fuel to reach that speed is itself a massive engineering problem. This is called the tyranny of the rocket equation. The more fuel you carry, the heavier the spacecraft becomes. The heavier it becomes, the more fuel you need to move it. That extra fuel makes it heavier still. The relationship between fuel and speed is exponential, not linear, and it gets worse very quickly. To reach even 1% of the speed of light using conventional chemical rockets, you would need roughly 10 to the power of 26 kilograms of fuel for every kilogram of spacecraft. That is more mass than the planet Earth. Not a practical solution. So how did New Horizons do it? The answer is that it did not carry enough fuel to reach Pluto on its own. Instead, it borrowed speed from Jupiter. 13 months after launch, New Horizons swung past Jupiter. The probe used the planet's enormous gravity like a slingshot, accelerating by an additional 9,000 miles per hour without burning a single gram of fuel. This maneuver shaved 3 years off the journey. Gravity assists are not a trick. They are genuine physics. The spacecraft steals a tiny fraction of the planet's orbital momentum, so small that Jupiter's own orbit is affected by an immeasurable amount, and converts it directly into spacecraft speed. It is free energy extracted from planetary motion. But gravity assists require extraordinary precision. To steal speed from Jupiter, you have to arrive at exactly the right point in space at exactly the right moment. Miss by a few hundred miles and the geometry fails. The launch window for New Horizons that allowed a Jupiter gravity assist was narrow. Miss it, and the journey to Pluto would have taken 5 years longer. Even with the Jupiter assist, New Horizons took 9 years and 5 months to reach Pluto. When it arrived, it passed at 12,500 miles above the surface at 36,000 miles per hour. The entire close encounter lasted only a few hours. It could not slow down. Carrying enough fuel to decelerate into orbit around Pluto would have made the spacecraft so heavy that it could not have been launched in the first place. So it flew straight through, capturing as much data as it could in a matter of hours, and continued outward into the solar system. After Pluto, New Horizons went on to reach Arrokoth, a small Kuiper Belt object about 4.1 billion miles from the Sun, making it the farthest object any spacecraft has ever visited on January 1st, 2019. Distance creates 2 more obstacles that do not exist for missions closer to home. The first is power. At Pluto's distance, the Sun appears as nothing more than a very bright star. Solar panels produce almost no useful energy there. Sunlight is about 1,000 times weaker than at Earth. This is why New Horizons runs on a radioisotope thermoelectric generator, or RTG, a device that converts heat from the slow radioactive decay of plutonium-238 into electricity. It produces only about 200 watts at launch, less than 2 old-fashioned light bulbs. That is the power budget for every instrument, every heater, and every transmission on the spacecraft. The second is communication. Radio signals travel at the speed of light. At Pluto's distance, a signal takes approximately 4.5 hours to travel one way. A question sent from Earth gets an answer 9 hours later, minimum. There is no real-time control possible. Every sequence of commands has to be pre-programmed and uploaded days in advance. If something goes wrong, the spacecraft has to handle it alone. Enjoy deep fact-check space stories? Hit subscribe and activate the notification bell. Otherwise, YouTube will not show you the next videos, and you'll miss what we uncover next. Proxima Centauri is the closest star to our Sun. It sits 4.24 light-years away, approximately 25 trillion miles. Voyager 1, the fastest object humanity has ever sent into deep space, is currently traveling at about 38,000 miles per hour. At that speed, it would take roughly 76,000 years to reach Proxima Centauri, if it were heading in that direction, which it is not. 76,000 years. The entirety of recorded human civilization is only about 10,000 years old. So conventional propulsion is not a discussion worth having. Chemical rockets, ion engines, even the most advanced plasma drives we currently operate, all of them land in the same range, tens of thousands of years of travel time. None of them are serious candidates for an interstellar mission. To reach Proxima Centauri in a time frame that matters, say within 100 years, a spacecraft would need to travel at roughly 3% to 10% of the speed of light. That is somewhere between 20 million and 67 million miles per hour. We've never come close to achieving that with any propulsion system. There are a handful of propulsion concepts that could theoretically reach the necessary speeds. None of them are easy. Nuclear pulse propulsion, the most studied concept for genuine interstellar speeds. A spacecraft detonates a rapid sequence of nuclear bombs behind a large pusher plate, absorbing the shockwave and converting it into acceleration. Studies from the 1970s, the Daedalus Project, suggested this could theoretically reach 12% of the speed of light, bringing Proxima within about 36 years of travel time. A crude version would require a spacecraft massing hundreds of thousands of tons and a pusher plate over 300 feet across. The engineering alone is generations away, and the international treaties banning nuclear weapons in space present an obvious additional obstacle. Laser sail propulsion, the most promising near-term concept. Instead of carrying fuel, the spacecraft carries only a large, ultra-thin reflective sail. A powerful array of ground-based or space-based lasers focuses a beam onto that sail from behind, pushing it to extraordinary speeds without any onboard propellant. This is the concept behind Breakthrough Starshot, a $100 million research initiative. The Starshot concept proposes accelerating gram-scale probes, each about the size and weight of a postage stamp, to 20% of the speed of light, or about 134 million miles per hour. At that speed, the journey to Proxima Centauri takes roughly 20 years. Add 4 years for the signal to travel back to Earth, and data from another star system could arrive within a human lifetime. The challenges are significant. The laser array required would need to deliver around 100 gigawatts of focus power. Interstellar dust particles hitting the probe at 20% of the speed of light carry the energy of small explosions. The communication system must fit inside a spacecraft weighing a few grams. None of this is impossible, but none of it exists yet. There is one obstacle that almost never gets mentioned in discussions of interstellar travel, and it may be the hardest one of all. Getting a spacecraft up to 20% of the speed of light is one problem, but getting it to slow down when it arrives is an entirely separate problem of equal difficulty. In space, there is no friction. Once a spacecraft reaches its cruising speed, it stays at that speed indefinitely with the engines off. This is useful for long journeys. You only burn fuel at the beginning and end, but it means the deceleration phase requires exactly as much energy as the acceleration phase. For the Starshot concept, this is not an issue. Those probes are not designed to stop. They fly past the Proxima system at full speed, photographing whatever they can in the brief seconds of closest approach, then continue outward into interstellar space forever. They are essentially very fast cameras on a one-way trip. But for any mission that needs to enter orbit or land or be crewed, the deceleration problems becomes catastrophic. If a spacecraft accelerates to 10% of the speed of light and then needs to slow down on arrival, it needs enough fuel for both maneuvers. Under the rocket equation, this does not double the required fuel, it squares it. The mass of fuel needed becomes so enormous that it defeats the entire premise of the mission. One proposed solution is to use the destination star's own light as a brake, a laser sail running in reverse, with the star's photons pushing against the sail from the front as the spacecraft approaches. In theory, this could provide gentle deceleration without any onboard fuel. In practice, it requires extraordinary precision in sail deployment and has never been demonstrated at any scale. This is the fundamental challenge that separates a flyby from a true interstellar mission. Flying past a destination is hard. Actually arriving, slowing down, entering orbit, sending back meaningful science over years rather than seconds is a problem of a completely different magnitude. Reaching Pluto took 9 years, a gravity assist from Jupiter, a flyby measured in hours and 50 years of planning. We have never gone back. Reaching Proxima Centauri with any technology that currently exists would take longer than human civilization has existed. With the most optimistic technology under active research, we could send a gram-sized probe that would arrive in 20 years and return data in 25. Nothing larger, nothing crude, nothing that slows down. These are not failures of ambition or funding. They are the honest result of the physics of moving objects through space, and the distances involved are so vast that even the speed of light begins to feel slow. The universe does not scale with human expectations. The solar system alone is large enough to require years of travel with our best technology. The nearest star is 6,800 times farther than the farthest object any spacecraft has ever visited. That is not discouraging. It is clarifying. Understanding exactly where the difficulty lies, the rocket equation, the gravity assists, the power constraints, the deceleration problem, is the first step towards solving it. And the fact that we are already discussing real engineering proposals for interstellar probes rather than pure theory means the conversation has shifted. We are not at the beginning of this story. We are somewhere in the middle of it. We covered how long it would take to cross the Milky Way itself, and why even the speed of light is not enough. Watch, how long would it really take to cross our galaxy? The numbers will permanently change how you see the night sky.